Good evening. Am I audible?
Yes, sir, you are.
Okay. Is the volume okay?
Yeah.
All right. Okay. Okay. So what we'll do is we'll continue from where we left. Okay. So we saw some brief history of neural networks on Monday. I'm not going to go over that. Okay. So and then we talked about the motivation for neural networks via logistic regression. Basically, you have a linear combination followed by a nonlinear activation. That is the basis for logistic regression, and that is also going to be the basis for a single neuron, right? So just take a linear combination of the inputs, and that is what we call pre-activation, just a slight change in terminology. And then when we apply the activation function on top of the pre-activations, we get the activation, right? So the activations are input for a neuron, and these come from the previous layer, and the activations are going to be the output produced by a neuron. Okay, and this is so if you put together a network of such neurons, we get a neural network. And then what we mentioned was that we'll be looking at only feed-forward networks. So all connections will be from left to right. They'll always move forward. There won't be any loops. So this is, if you think about it in graph theoretic terms, this is a directed acyclic graph. So we look at two problems, both supervised, which is regression and multi-class classification. Binary classification is a limiting case of the second one. Notation you all know. The neural network can also be thought of as a function, just like we have been doing for many of the other classification models or regression models. A neural network can be seen as some kind of a function that takes an input and returns some output. Okay, so we looked at three components. One was the layer, the other is weights and biases, and then the activation functions. So the layers are probably the most important part of the network. So each layer has a set number of neurons, and the input there, a neural network should have at least three layers for it to be meaningful, for it to be even called a neural network. One is the input layer and the other is the output layer, and at least there should be one hidden layer in between. Okay, so the number of neurons, so sometimes these are called neurons, sometimes these are called nodes, right? We can use them interchangeably, but we'll stick with neurons. The number of neurons in the input layer will be equal to the number of features in your problem. So if you're solving a regression problem which has say 100 features, you will have 100 input neurons, and you will have a single output neuron corresponding to which will output the real number. You're solving a classification problem, let's say with 3 classes with the same input space, your output will have 3 neurons, right? So that is the idea of arranging neurons in layers. So this network has one hidden layer. This has two hidden layers. The number of hidden layers is a hyperparameter, right? So this is something you'll have to determine based on your validation set, right? So some kind of cross validation, hyperparameter selection has to be done. In fact, most of your time will go, when it comes to neural networks, most of your time will go in hyperparameter search, right? So The basic idea is quite simple. You need to stack certain number of layers, but you never know what the number of optimal layers is going to be, right? So sometimes it may be 3, sometimes it may be 5, right? It depends on the problem you're solving. So this is just the way we are going to index our layers, nothing special here. SL will be the number of neurons in a particular layer, right? So for S0 will be the input and S capital L will be the output. Everything else is something that again you have to determine by using the validation data set, right? So number of neurons is again up to you. Right, so weights, as we said the other day, is the importance of connections between neurons, right? So between a neuron in layer L minus 1 and neuron in layer L, how important is the connection? That is determined by your weight. In graph theoretic terms, we again mentioned that this becomes a weighted directed acyclic graph, right? So it's a weighted DAG. Yeah, any questions?
So weights actually emphasize the importance of features, right?
Sorry,
Weight emphasize the importance of a feature instead of edge, right? Because each neuron is a feature. So we apply weights to these neurons, so that will tell its importance, right?
Right, you are right. Yeah. So the importance of the connections. So when I say this, I am talking about it from a graph theory kind of view, right? So where the edge is typically the edge between two nodes in a graph, right? So if you look at it that way, then the weights represent the importance of connection. But you are right in the sense that since we are doing machine learning and these all represent features, the weight, it's more appropriate to call the weight as the some kind of a measure of the importance of that particular feature, right? But we have to also remember that it's not just that particular feature, the importance of the feature's contribution to this node, right? So we always talk about weights across layers, right? It's not just weight is not something that is an that is connected to just one feature. It's connected to two neurons across layers. So we have to emphasize that part. Okay, so if you put all these weights together.
So one more doubt.
Yeah.
In the layer L1 and in the layer L, so the layer L is always going to have less neuron than level L minus 1, right?
Not necessarily. So it appears that way because the images, the network that I have drawn is just for illustrative purposes. The actual neural networks that you are going to work with may have different. So the previous layer might have less number of neurons and the next layer might have more number of neurons.
So how is that decided? That is also a hyperparameter?
Yeah, the whole thing is called it's called network architecture, right? So this is called a network architecture. Architecture meaning how many layers are there, how many neurons are there in each layer, what are the kind of layers used, right? So all this comes under the this is a big step when you are building a neural network, deciding the network architecture. So there are several architectures out there which machine learning scientists have already come up with. But if you're working on a new problem, right, you could come up with your own architecture. So you'll have to decide all this from scratch. Okay, so it is not, so the image that you see in front of you is not necessarily the golden standard, right? So this is some illustrative example and not applicable for all problems.
So when we are solving a problem like through ANN, so what we do, how do we mention all this? Like
How do we mention the number of layers you're asking?
Number of layers, the number of layers, number of neurons in each layer. How do we do that?
So that will become a part of your implementation. So if you define a ANN class, then all these will go as parameters of uh, the class. So for example, I have to have n underscore layers, and I might choose to represent. So the questions of representation come in, right? So how do I represent the number of neurons in each layer? I might choose to represent it as a list, right? So typically that's what we have done. So if you look at, okay, so it's good that you brought this up. So if you look at the implementation, which I don't know if we'll do today or on Saturday, but if you look at the implementation, we use list S, Python list S to denote the number of neurons in each layer. So for example, S of 0 will be the input, number of neurons in the input. So if there are 10 inputs, S of 0,
S of 0 will be equal to the number of features.
It will be equal to the number of input features. Yeah. Right. And if there are 20 hidden layer neurons, then S of 1 will be 20. And if there are no other hidden layers, and let's say this is a 3-class classification problem, S of 2 will be 3. So I would specify n layers to be 3, and corresponding to that, I will have to specify this list S. Right. So that would be my model call, right? So this is how I would initialize a ANN object. And then
and this was also taught in the implementation part. So I have not seen that part yet. So that's
right, yeah. So this will come up later, right? So when we implement it, we'll see how these notations will carry out. So that is the advantage. The S, whatever SL minus 1 we say, that will carry over. So it would be SL minus 1 comma SL. So if you look at them as NumPy arrays, your weight matrix layer L, if you will be equal to this. Right. So when we come to the implementation, these things will become more explicit. Okay, so the whole thing is, just to repeat, this whole thing is called network architecture, and this is something you'll have to figure out during the training process. Okay, so that is the weights. Now, if you recall, I made one statement on Monday, which is that the weights are for the connections or the edges between neurons, but the biases are for the neurons themselves, right? So each neuron in each layer has one bias term associated with it. Okay, so the bias is not defined between or rather the bias is not defined for the edges, it is rather defined for the neurons themselves. Okay, so there is one bias associated with each neuron. So one way to understand, in case some of you are wondering what the bias term is, why is it called a bias? So assume that all the inputs are set to 0, right? A1, assume that A1 equal to 0, A2 and A3 are 0. In such a case, is there some, what the neuron will output is what we term the bias, right? So if the bias is, say, positive, then that means that the neuron is biased, positively biased, right? So if I don't, even if I don't give it any input, what will it output, right? So we call that bias, and that is the value B. Okay, so this is kind of a new point. In case you are wondering why we call this bias, this is one way to understand it. Okay, so that is, so far I think you all, I hope you are all with me. Are there any
questions? This bias, how will we what will you input out there? I mean, suppose we take a classification problem.
Bias, you will initialize the biases to some value. Typically,
Okay. So it'll be some random.
Random value or zero.
Okay.
But yeah, we'll come to initialization. Typically, it's some random value. So okay, so that is what we had for. That is the network architecture part. Now we come to what we call the forward pass, right? So forward pass, if you recollect, forward pass is this is what it does. So given an input, compute the output, right? So this is what we need to do. So how do you do that? That is what forward pass is concerned with. And if you have an input vector, right? If you have three features, let's say, then A transpose W plus B transpose, right? This is just a linear combination, AW sigma WA plus B. Same thing written in terms of vectors, right? So I hope there are no questions here. If there are, please stop me, otherwise I'll just move on. So this is for one training example. If you stack together n training examples, then you have a matrix form of this, the whole thing, right? So AW plus B. So if you, this is not new, you have already seen this. This is nothing but HW plus B, right? So whether it's linear regression or logistic regression, it's the same form. Instead of calling it X, I am calling this A. I hope this is okay with all of you. Okay, so once you have the activations, pre-activations, you just go ahead and compute the activations by applying the activation function element-wise. Okay, so that is what you do. There are different kinds of activation functions. I'll skip the part of why you need them because we covered it last time. But the most popular ones are Sigmoid, TANH, ReLU. ReLU by far, it's kind of more popular than the other two, right? Owing to its, so empirically it has been verified that ReLU works extremely well. So there is that empirical backing. Also, you have this nice property of ReLU being computationally very easy to evaluate, right? So you just need to compare if the input is greater than 0. That's all you need to do. Whereas when it comes to Sigmoid or TANH, you notice that you have to compute an exponent and here multiple exponents, right? So all that is there, whereas here is just a simple Boolean comparison, right? So computationally it's advantageous, and also there are a few other good properties. So this is the graph of Sigmoid. From the exam perspective, it's good to know it's good to remember the graphs, right? So Sigmoid, you already know the formula. TANH, you don't need to memorize the formula, but you need to know that TANH, the range of TANH is -1 to 1. That is something you'll have to remember. And at 0, TANH takes the value 0. I think this is also something you need to remember. But other than that, the formula you don't need to memorize. ReLU, you have to know the formula because it's simple enough, right? So yeah.
So one doubt here.
Yeah.
These activation functions, they are associated with every neuron. No?
Activation functions are associated with every neuron. Yeah.
And every neuron, in no matter in which layer they are, if I set my ANN to have activation function of ReLU, so every neuron will have activation function as well, right?
Every neuron will, you will apply this ReLU on every neuron, but for the last layer, where you will have a different activation function.
There I will have a different activation function.
The activation function of the output alone will depend on the problem you are solving. So if it is regression, you will just have the identity function. If it is classification, since you want a probability distribution over the k classes, you will have softmax. right? So that is the only difference. But for all other layers, you will have this. Okay, so
I just one clarification. I
yeah,
think people who are doing the MLP will. And so in MLP, what we have is when we give that the classification for neural networks, the output is a logistic. Now here we are saying it's a softmax.
output is
So
a stick, is it? I mean, like two classes, you're saying. Sigmoid of something is what is.
probably it's I don't think it's taking two classes, but what I went through is saying the output is logistic, and for this regression, of course, it's identity. So
Okay.
I don't know if you have any idea about that.
Okay, by logistic, what do you mean? Like
The sigmoid function. The sigmoid function is the output.
As the output.
Yeah.
Okay, so that might be the case if it's binary classification. So also, yeah, even if it's not binary classification, sometimes sigmoid can be applied for each node in the output class. But if it is binary, it becomes quite clear, right? So, for example,
Yes.
You have only one node in the output class. This we discussed the other day, right? You have only one node for classification also, and that is a sigmoid. So sigmoid activation that works.
Okay.
Right. So that also works. If you look at few other references, they would have used sigmoid instead of softmax even for multi-class. So, for example, this very popular textbook, online textbook for neural networks, I think they use, if I'm not wrong, they use we have the sigmoid here. Let's see where they. Yeah, I mean, you can refer to this. I think they would have the initialization feed forward SGD backprop evaluate. Yeah, so see, they have used this particular textbook uses sigmoid throughout, right? So it uses sigmoid for each class, even for multi-class classification.
Right.
But depending on that, I think the cost function also they would have changed. But it's not wrong, right? Whatever you studied in MLP is also valid.
Okay. Right.
For the MLT course, if it is multi-class, then unless specified, it will be softmax.
Softmax. Okay. Thank you.
Okay. Okay. So yeah, how do we finally compute the forward pass? We do it iteratively. First, compute the pre-activation vector, sorry, matrix, and then apply the activations. And only catch here is that for A0, it will be there won't be any activations as such. The input itself will be the activation, and for the final layer, the activation function will be linear or softmax depending on which problem you're solving. Okay, so this is where we stopped. I think probably I took too much time. So any doubts so far? We'll continue from here. Okay, so if you have understood till this, now it's pretty much the same old story of how do we learn the weights, right? So finally it comes down to that. How do we learn the weights? Again, we have to look at the loss function, right? So we need to define a loss function which will give us an evaluation of how good the model is currently, right? For regression, it's familiar squared error, right? And for in NumPy, you can very easily calculate this, right? As y hat minus y transpose y hat minus y, or this way, right? Both are the same. The loss for classification is actually quite simple, but the way I've written it is, it may seem a bit messy. So Do you all get what is written here?
This is similar to softmax, right?
This is similar to, so yeah.
So wherever there is a matching, after one hot encoding, wherever there is a match,
exactly,
corresponding probabilities multiplied.
Yeah. Did everyone get this? Can I move on, or do you want to spend some time on this?
It's basically the np dot where y hat equal to y. The same thing, right, sir?
It is. So it is. See this. I won't say where it's equal to y. So see, this is the numpy. This is what it means in numpy.
Okay.
So what we are doing essentially is, for each row, for classification, each row represents one example, and each row of y hat represents the probabilities of the k classes, right? And each row of y will be a one hot vector. So only one element in y will be 1, rest will be 0. So if you look at this y element wise product log y hat, it will be a sea of zeros, and there will be just one non-zero entry in each row.
So can you give one example? Can you draw the matrix?
Yeah, so it will look something like this. So if you are solving a, let's say, 3-class problem, then if you are solving a 3-class problem, and no, I don't need one more. Yeah, so you have, this is y, right? Y will be the one hot matrix, right? One hot encoded matrix. So let's say the first example has label 0 or label 1. Second example has label 1, and third example has, say, label, right? So these are the labels of those data points, right? You have so how many examples do you have? We have 5 examples. So we have 5 examples and 3 classes. Now your, oops, some other random symbol came up. Okay, so your output of your neural network will be y hat. Okay, so this is important. The neural network's output is y hat. Okay, the forward pass is now over in some sense. Now we are computing the loss. So your y hat will be a matrix of probabilities, right? And let's say the probability of this being 1 is 0.3, right? And this is, say, 0.6, and this is 0.1. This is the first example. These are the probabilities computed by the neural network, right? So this corresponds to the output at node 1. This is output at node 2, output at node 3 in the output layer. Okay, let's say here the network computes a probability of 0.2, 0.1, and 0.1.
This is what we get from the softmax function.
This is what we get from the softmax, yeah, at the output layer.
Right.
Okay, and let's say here it is 0.3, 0.4, 0.3.
So
Yeah.
we see 0.3 in the first row, first column. So 0.3 actually means that 0.3 is the probability of getting 1 in first row, first column, right?
0.3 here you're saying, huh?
Yeah, it is the probability of getting 1 in first row, first column.
Probability of, yeah. So to put it more in practical terms, I would call it this, right? So y hat of I'm using 0 indexing. 0, 0 is the first row, first column, right? So that is 0.3 is the probability of class 0 for, okay, I'm using, I assume that, okay, this alone I'll call it 1. This is clear, right? Each row corresponds to one training example, right? So first row corresponds to first training example, and each column corresponds to one class, right? So if I use 0 indexing throughout, just to be clear, for the 0th example, the first element in that particular row will be the probability that the network thinks that this example belongs to class 0.
So we'll basically take the maximum of
Yeah.
the row.
Yeah. For inference, we'll do argmax across the column.
Row. Column, yeah. Column in terms of, yeah. X is equal to 1.
Yeah, X is equal to 1.
Right.
Okay, so when I say, I hope this is clear, right? So far it's clear. So when I say the loss is equal to y hat, so I do a log of y hat. Okay, so I do a log of y hat.
Why?
We do that because of it's called, so that the loss is, in this case, it's called categorical cross entropy. So
okay,
right, if it was binary cross entropy for sigmoid, sorry, for logistic regression, because it was 2 classes, it was binary cross entropy. Since we have multiple classes, it's categorical cross entropy.
Right, sir. Right.
Okay, so this is categorical cross entropy, and so.
Hello, sir.
Yeah.
Sir, here I have a question. In this part, this log of y hat, we have the few elements which are 0.
In y hat, yeah. No, sorry, yeah. It looks like that, but it's safe to not put them as 0. So we have.
Actually, sir, like today I was implementing a logistic regression model only.
Okay.
In that process, I was getting, like, somewhere I was getting this y hat in where there are few elements which are 0, and that is pretty much normal, no, sir? Some element might come 0, no?
For you're saying neural networks or logistic regression?
For logistic regression, like, not for neural networks. Only I am talking about only this log of y hat.
Okay, so it may happen, but in theory it should not happen, because sigmoid log. So you're taking log of sigmoid of z, right? Ultimately.
Yep. Yeah.
So in theory it should not happen, but in practice it can happen if your z value is too high. So it will cause overflow, right?
Yeah. Okay. That is overflow. I was getting that error, but I was not able to understand that.
Right, overflow or underflow. I think if it's too high, overflow. If it's too small, then it may become 0, and you might get. So if you take log of 0, it might complain that. Right. So here we have taken a safe case of. So let me just call this, just to keep things simple, I'm just going to sum all the elements of this matrix. That's the loss.
Just one question.
Yeah.
In the softmax, why do we take the mean? Because sum makes more sense. In the softmax implementation for the loss function, we take the mean.
Mean where? Sorry, can you tell me where?
So if in the softmax, that implementation collab, so Professor Tendulkar has taken the mean as the, and so I don't understand, because sum should be the correct.
Yeah, sum should be.
Yeah, I mean, the implementation there, he has calculated the mean of this y into log y hat, and correspondingly, gradient is also divided by n.
Oh, okay. Right. So he's taken the mean because there are n examples, right? Actually, we have missed out. In a sense, we have missed out the n. It is in practice, some of them add the 1 by n also, right? So see, the loss is for n examples. If you want the loss to be, if you want to interpret the loss properly, you have to divide by n, right? So I'll remove this, but you get the point, right? So if there are more examples, then your loss will scale according to that. So that's why he has taken the mean rather than the sum.
Okay.
Yeah, so just as an extension, so generally in exams and all that, OPP, are we expected to calculate the average loss or?
No, just calculate the sum if there is a.
Okay, if it's average loss, you will specify somewhere, right?
Specify
I
it,
mean, we'll assume it will be the sum of.
It will be the sum. Yeah.
Okay, sure.
Okay, so the categorical cross entropy is something like this. So.
Sir, what is exactly is happening here? The symbol, I don't understand that basically.
Yeah. So we will come when we compute that, it will become clear, right? So this is nothing but it's element wise product, right? So we have two matrices, right? Log of y hat is one matrix. So we are multiplying two matrices element wise. So if I just write this as normal product, that will become matrix multiplication. So in order to avoid that confusion, this is called
Hydromet or something.
yeah, this is called Hydromet product. So nothing but element wise product, right? So what would this mean? This would mean the following. So you take this and then you also take this, right? So of course you have to compute the log of this, which I'm not going to do. How shall we do it? I don't think we need to compute the exact values. I'll just, so we are going to multiply 1 with log 0.3, right? So this will just be log 0.3. Okay, so everything else in this row is 0. So I don't need to worry about log computation, right? So even if I take the log, this is going to just become 0, right? So this is log 0.7. This is log 0.4. This is log 0.8. This is log 0.5, right? So L equal to the negative of this. So sum of this basically, right? So let me not write L here. This Hydromet computation, is it clear what we are doing?
So
Yes,
this
sir.
matrix will be 0.3, the third row, log, the log. Yeah. The last element will be 0.3, right? Not 3.
You mean this one?
No, the log matrix on your right hand, on your left hand side. Left hand side is matrix, the third row.
You mean this one, the third
No,
row?
the last element.
Okay. Sorry, yeah, this is 0.3.
Right.
Okay, so this is yeah. So
And so when we are summing up all of them. It's not
Yeah.
axis or anything like
no,
that, right?
we are summing up all of them. So see, there's actually a beautiful loss. There's a way to understand it. Once we understand it, it will become very clear. What we are saying is, again, we have to focus element by element, right? So if you focus on, I'll add the minus sign also so that it becomes complete. So focus on the first example.
And this is natural log, right, sir?
This is the natural log, right? So the first example, this is the true label, right? True label is what? Class 0, right? True label is class 0. Now, what is the contribution of my loss here? Of what is the contribution of the first example to the loss? It is minus log 0.3, right?
Yeah.
Okay, so if this quantity is So for this, we need to understand how this works. Okay, log of a fraction is negative, right? So minus log of that fraction is going to be positive. So loss is always positive. So this first of all, this term is positive. The next thing is, if you all recall the logarithm function, the closer we get to 1, the higher it becomes, right? Or more negative it becomes, depending on which side you approach.
Yeah, yes, sir.
Okay, so the closer I get to what am I trying to say?
So basically, this log of the smaller number is, I mean, when it is less than 1, it is more negative.
Yeah, when it is less than. Okay, so sorry, I kind of one second, I kind of messed up this part. Maybe. So we have ln x, right? So sorry, what I meant was the other way. And okay, where is that log fellow? Yeah, so see, in fact, let us plot minus log x, that's easier, right? Let's plot minus log x. Okay, so minus log x is in some sense our loss, right? So the closer we are to 1, the smaller the loss. Okay, so closer, so x minus log x, here x is what? X is the probability that I am predicting this as class 1. So this 0.3 value is the probability. So the closer my probability is to 1, the lower the loss.
Right.
Right?
Clear.
Okay, so the closer I am to 1, the lower the loss. So note that for the other terms, the contribution of the loss is 0. I don't care basically. I only care about what my network says about my true label. My actual class is class 1 or class 0. What does my network say for that? It says that it is 0.3. So I am only interested in the loss corresponding to that. So I am only penalizing I'm only penalizing a particular class. Do you see that? I am not penalizing the other things. Right? So is this picture clear to everyone? What the loss actually is trying to, what it means in neural networks, this cross entropy loss?
Yes, sir. Quite clear.
Okay, so so just to reiterate, if it is close to 0, then that means this will be a very high value, right? So eventually there will be one non-zero value contributed by every training example. There will be, if there are n training examples, there will be n such log values, and if you add all of them together, that is what this loss is. Okay, so that is the categorical cross entropy. So once you have the loss, how do you update the weights? You have to compute the gradients, right? So okay, so here's the big challenge, right? This was a big challenge for the whole neural network community, and this is what Jeffrey Hinton, if you remember the person I was talking about class, which he was the one who kind of popularized the method to compute the gradients, and that algorithm is called back propagation, right? So do you all see why there is a problem here? Why is this gradient computation going to be a problem?
Is it because of the network?
Because of the network, right? So what? So
Because-
what challenges will that pose?
Sir,
From-
like in the
from-
middle of the network, we can't be sure what is the actual output will be.
Right, right. Yeah. So you are right. So the network, what it does is it kind of, we are not sure how to compute the gradient, right? So in logistic regression, it was very simple. So the final functional form was something like W transpose X, right? And I need to compute the gradient of the loss with respect to W, and the form was very simple, right? You have a sigma of W transpose X, and once you know what the loss, what the gradient is with respect to this value, then you just need to multiply that with X, right? So it was quite simple. But here
Also, sir, the W keeps changing here, right? That also may cause a problem. The weights at every layer.
the weights at every, so right, so the weights at every layer will keep changing, and because they are arranged in the form of layers, it's not exactly clear. I mean, immediately it's not obvious how you will compute the gradients, right? So
just more fundamentally, just drawing comparison to softmax regression, there we are differentiating with respect to every single weight. So like W11, W12, W13, and so on.
yeah,
Right, and each weight can contribute to more than one activation output.
each weight can contribute to.
So as in each weight will essentially map to
more than one. Yeah, you are right.
And therefore we have to differentiate, keeping in mind that. So it kind of goes back as a network.
Yeah.
But here the issue is that it is even further complicated because there are more layers and more weights, different weights that are associated.
Correct. Yeah.
Okay.
You are right. Yeah. So that is the big problem, right? So you have multiple channels of contribution, and how do we compute that? So we, to some extent, we'll address this. Okay. So the basic idea is that the chain rule, right? So chain rule we have been seeing from the very first week. Right from linear regression, we have been using chain rule to compute the gradients. So there's no big deal there. But the beauty of this back propagation algorithm is that in one go, we'll be able to compute the gradients of all the weights in a particular layer, and we'll be able to do this layer by layer. Okay, so if you want to understand back propagation, the easiest way is to go for an example, and right. So consider a regression problem. Let's work this out. You have a regression problem with, it's a very simple setup, right? You have your training example has just one feature, right? X, and you have to produce one output. Okay, so that is your data. You have many such data points, but we'll just see how this whole thing works. So your network architecture is going to be like this. You have input layer, which is just this X. You have two hidden layers, right? And you have one output layer. Okay, and each layer has exactly one neuron to keep things extremely simple. So the network is something like this. So is this image clear to everyone? What's happening here?
Yes, it's clear, sir.
Clear, right? So you have some input X, and then it passes through one hidden layer to become A1, and then through another hidden layer to become A2. Finally, the output layer, it is A3. A3 is nothing but the output of the network, right? And we call it Y hat. Okay, so
What is state one?
Z1 is the pre-activation, right? So we'll compute that. So we'll compute one by one. So the first hidden layer, can someone tell me what will be the first thing we do in the first hidden layer?
W1 into X.
Okay, so W1, I just call it AA0 just to be consistent, plus B1.
B1.
Okay, so this is what?
Z1.
This is Z1, right? So this is the pre-activation at the first hidden layer. Okay, so this is the pre-activation. Now next step would be what?
Do the activation of this. G of Z1 will be equal to A1.
Right. So this is A1. So we are done with the first hidden layer, right? So we can now just repeat this. So this will be what? Z2 will be what?
Z2 equal to W2 A1 plus B2.
A1, right?
Yes, W2 A1 plus B2 and Z2 equal to G of. Okay, so this is second hidden layer and there's no third hidden layer. At the output layer, what would it be?
W3A2
Okay, W3A2
plus B3.
plus B3. This will be
Z3. Or yeah, Z3.
Yeah, I haven't added that. So there will be a Z3 also.
Which, since it's regression, it will be an identity, right, sir?
Right.
Yeah, since it's regression, it will be an identity. So let's just call it y hat equal to G of Z3, but let's just stick to
Z3.
3, right? Y hat is, sorry, yeah, A3 equal to A3 equal to Z3, right? So it's all the same. So this is actually G of, if you want an extra step, just to make things clear, let it. So yeah, this should actually not come under, let's not call it, let's not put it here. So let's separate this out, right? So y hat equal to A3 is something we say it's the output of the network, right? So network output is this y hat equal to A3. Okay, so this is what we have done, right? So this is the forward pass, right? So much for the forward pass. Once we have the forward pass, we need to compute the loss. So what will be the expression for the loss? For a regression problem?
So it will be that
SSC
minus,
will
sorry, y minus y hat transpose y minus y hat.
Right. Okay, so since we are dealing with scalars here, I'll just they're all real numbers, right? It's just scalars. So I just say this is okay. So this is just this will be the loss. Okay, now we need to compute the gradient. So this is what we need. This is what we need to look at. Right? This is new to us. So how do we do that? This is the whole question. So let me write down all the gradients that we need. We need the following gradients, right? So W1. So we have 3 weights, right? So W1, W2, W3, and also the bias. So bias is important, but let's not worry about computing the gradients for the bias now, right? So we need these 3 gradients to update the weights. Okay, so what do you think is going to be the first step?
First will be DL by DW3, right? And OL by OW3.
Okay, right? So see, the first thing to note is that my loss is defined in terms of y hat and y. Now what is a variable? What could vary here in this example?
Y hat.
Y hat is going to be the variable, right? Variable in the sense I am given x comma y, right? So that the input and the label, true label, are kind of like constant, right? I don't need to worry about that. So what I need to worry about is the network's output, right? So that is what I'm going to worry about. So let's say we start with dou L by dou W3. So I'm going to write it as, right? So sorry, this is what dou L by dou y hat, right? Times what should I add here?
Dou y hat by dou W3.
Yeah, you are right. So is this step clear? I mean, this is, if you understand this, then you understand back propagation more or less. This is just chain rule in action, right? So 3 variables. See, W3 influences y hat and y hat influences the loss. So if you want to find how W3 is going to affect the loss, I need to go via y hat. Is this?
Sir, can you please repeat this part, sir?
See, this y hat. See, I need to come. What do you mean by this dou L by dou W3? What does this mean? So
Differentiate the loss with respect to W3.
yeah, differentiate. So it's the derivative of the loss with respect to W3. But if you look at it from a practical standpoint, what does it mean? This is what it means, right?
W3.
Keep all other parameters of the network fixed, right? Meaning keep W1, W2, B1, B2, B3 fixed.
Constant, right?
Right? So slightly perturb W3 and measure the corresponding change in L. This is what we are saying, right? This is what loss, this is what the partial derivative means, right? Everything else is fixed, and if you move W3 slightly, how does L change? That's what we want to compute.
Yes, sir.
Right? So okay, so this is what we want to do, right? So what I am saying is, if I slightly perturb W3, then since y hat depends on W3, how do we know that y hat depends on W3? See, y hat is what? A3. Right? A3 is nothing but Z3. So y hat is Z3. Let's just add that so that. So y hat depends on W3, right? So if I move W3, I'm going to move y hat.
Yes, sir.
If I move y hat, I'm going to move L.
Yes, sir. Yes.
So I am chaining these dependencies together and saying that if I want to know how L changes with respect to W3, I can go via y hat.
Yes, sir. Yes, sir.
Okay, so this is what we are doing, and so dou L by dou y hat is what?
That's just a y hat.
Y hat minus y.
Y hat minus y.
Right, so that is just y hat minus y. Dou y hat by dou y W3, what would that be? Y hat W3.
A2.
It is just A2, right? So it is just A2. Okay, so now we have computed the loss, the gradient of one weight, I mean the partial derivative of one weight. Okay, so we have this. Now the key idea in back propagation is that, and why it's called back propagation is that, once you have the gradients with respect to one layer, you can use the chain rule to back propagate it or send it back to previous layers. Okay, so that's the essential idea. Once I know the gradients in this layer, I can use them to find the gradients in the previous layer. And iteratively, I can keep doing this until I hit the initial layer. Okay, so let's do this for dou L by dou W2 also, and then we'll understand. This is what we need to compute. Okay, so I need to compute W2. So notice that W2 goes via Z2. Okay, Z2 goes via A2, and then A2 finally hits Z3, and Z3 we have already computed. So do you see the chain of influences? If I keep B2 constant, and A1 is anyway input, so A1 is treated like a constant. So if I change W2, that will impact Z2, which will in turn impact A2, and if A2 gets impacted, Z3 will get impacted. But I know how Z3 affects the loss, right? So what I'm going to do is I'm going to write this as dou L by dou Z3 is this.
So can you directly do that, or do you have to do G of Z3? Because
Yeah.
there is an A that comes.
Sorry, yeah. So yeah.
It's G of is it Z2 or Z3? I'm confused. Because there is a G of Z2, right?
Yeah. So we'll come to that, right? So, but this part, do you agree? Like, see, I want to find the gradient of loss with respect to W2 to Z2 to A2 to Z3, right?
Yeah.
Now, sorry, what I wrote earlier was correct. This is what I need to compute. So I need to know how I affect Z3, how the loss gets affected by Z3, and then Z3 with respect to W2.
Right.
So how does the loss change with Z3? So we computed dou L by dou W3. Now what do you think will be dou L by dou Z3?
Dou L by dou Z3 is already computed. No, we have done that, which is
That
what
is
we have done.
at
Dou L by this one.
Okay, so this is going to be what?
Y hat minus Y into A2.
See, that is
Water
dou L by dou W3.
Sure. Only water away. Mineral water is.
That with respect to W3.
Rabba, Kata Venkat Reddy. Khatam.
Right. So see, I think I'm missing something. Dou Z3 by dou W2. Where is Z?
Z3 is same as Y hat.
Yeah. So dou L by dou Z3 is just Y hat minus Y. Is that fine?
Yes, sir.
Now dou Z3 by dou W2 is what?
Dou Z3 by dou W3.
Okay, then we have to substitute A2 with Z2 with G of Z2.
We'll have to create another chain for that.
Yeah, we'll have to create another chain. So
That is dou Z3 by dou W3 into dou W3 by dou G of Z2 into dou G of Z2 divided by dou of W2. Is that how it goes?
Right. So dou Z3 by dou W3, right? So dou Z3 by, this is one thing. Now this is dou W3 by W3 now depends on what?
G of Z2.
Okay, so which is A2, right?
A2.
It is A2.
A2, right.
Now dou A2.
W2.
Okay, is that looking correct?
Sir, I didn't get the first y hat minus y. How did you get that, sir?
That is dou L by dou Z3, right?
Yeah.
Dou L by dou Z3 is, since Z3 is y hat, it is just y hat minus, this is dou L by dou y hat in some sense.
Okay.
So I think it's better to consistently use A or Z. I think we're mixing up a little both.
Yeah, you are right. So let me go back to the slides. What I have done there, I think it's better to refer to it first and then explain it here. So what have we done here? Yeah.
We are kind of doing the same thing.
Yeah, but we are doing, as Kaushik said, dou L by dou A2 first. A2 Z2 Z2 is W2. Okay, so like what have we done here?
Yeah, we've not done A Z2. We have directly gone to W2.
Instead of A2, right?
No, that is correct. I think in the chain.
In the chain,
it might be better to just write the whole chain, right? So, I mean, just before putting y hat minus y, I mean,
okay,
if you don't
yeah.
mind, if you just write the whole chain, it is dou L by, first dou L by dou of Z3.
Okay, yeah, that is good idea. So dou L by, okay, let's write it this way, yeah.
Yeah, but just that A3 and Z3 are the same in this
same,
case.
right,
So
yeah.
but we can still write it, I guess. It's going to give you one only.
Okay, let's in fact remove this part. It's just one big chain. Dou L by dou W2 is, I start from A3, right? I start from A3 since that's the output of the network.
Then dou of A3 by Z3, which is going to be just 1.
Yeah, we have to add that as dou A3 by
Z3.
Okay. Now, yeah, rest of it is the same, right?
A2 and then A2 by Z2.
A2 by
last one. Last one will be A2 by Z2 and then Z2 by W2, right?
Right. A2 by Z2 and okay, let's just see this ones. L with respect to A3, Z3, Z3 depends on W3, W3 depends on one second. So what is this?
Change in A2 will change W3, right?
Change in A2 will change W3.
So can you just bring back, bring this, just copy this picture
yeah.
and paste it?
Okay, yeah, that is also a good idea. Many good ideas. So that is much better. So see, what are we saying? We need to find L, the effect of W2 on L, right? So what are we keeping constant? Everything else, see, everything else remains constant except W2. A1 and B1 are going to be constants because they are input. They are going to be the input to your system, right? Now A2 is going to change because of W2. Z2 is going to change. Okay, W2, let's go this way, right? Let's go right to left. So W2 is going to change Z2. Z2 is going to change A2. A2 is going to change. A2 is not going to change W3, right? This part alone I am not sure. See, A2 is not going to change W3, right? A2 is only going to change Z3. Right, so
Okay.
A2 is going to change Z3, Z3 is going to change A3, A3 is going to change N. Is that sequence fine?
Weights don't come. It's only at the end that we get the weight.
Yeah, so the weights, by the definition of the partial derivative, everything else except W2 is going to be fixed. Right, so what is going to be affected by W2 is the activations and the pre-activation. So W2 will affect Z2, A2, A2 will affect Z3, A3, A3 will affect the loss. Okay, so dou L by dou A3 will be y hat minus y, right? So I hope this is clear. Dou A3 by dou Z3 is what? It's the identity, right?
That's just one.
That is just one. So this we have computed these two. Now dou Z3 by dou A2. Z3 is what? W3 A2 plus B3, right? Pre-activation of this final thing is A2 into W3 plus B3. So what is dou Z3 by dou A2?
It'd be W3.
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 W3, right? So this we have computed.
So, but that will depend on the A2 function, right? No?
That,
or is it in the next one? Okay.
That is the next one, right? So this is where the G dash. So this is what? What is this?
So that will be whether it is the tan H function or.
Yeah, so this will be nothing but the derivative of the activation function.
Right.
Okay, whatever it is, it will be its derivative. And then dou Z2 by dou W2 is what? How does weight affect the linear so the pre-activation here?
It will be A1, no, sir?
It will be A1, right? Okay, so if we simplify it, I just want to make sure that we are consistent with the slides. We are getting this expression, and let's y hat minus y W3 G prime of A1. Okay, so here we don't have a 3-layer thing, so
Don't have W3.
yeah, we don't have a W3. Okay, so see, in all this, the back propagation should not get lost. So see, maybe it would have been better if we had taken up a two-layer example itself, but it's okay. So is this part was clear, right? How we compute dou L by dou W2?
Yes, clear, sir.
Okay,
Yes.
so here if you notice, we had to rely on particular gradient, which is I want to pinpoint that. Which is dou L by dou A2. So if you think about this, This whole thing is what?
Dou L by dou A2.
This is dou L by dou A2, right? So, okay, so this is where the whole idea of back propagation comes. So, you, while computing dou L by dou W3, you also compute dou L by dou A2, which is actually not too hard. So, see, dou L by dou W3 was what? Y hat minus Y into A2. Dou L by dou A2 will be what? Y hat minus Y into W3. You all see that?
Yes, sir.
Okay, so
Yes, sir. Yes,
while computing this fellow, we have to compute this fellow also, which is dou L by dou A2, which is nothing but W3, right? So now, if once I compute dou L by dou A2, I just make use of that to compute dou L by dou W2, which is in the previous layer, right? So this is how I back propagate my gradients or errors, but this is where the idea of back propagation comes.
Sir, one thing,
Yeah.
this dou L by dou A2, will we like, do we calculate that in the previous part or this part?
No, we compute it along with W3. Along with W3, that is, the reason is as follows, right? So, see,
Because
yeah,
when we are changing W3, it is not affecting A2. So it is only affecting A3, Z3 like this, A3, Z3, Y hat, all this.
right,
But
right.
it's not affecting A2. So should we do that in the previous part or should we do it in this part only? We will do it beforehand, but in this part, I am saying.
We will do it here only. I get your point. Your point is valid. So, see, when we say dou L by dou A2, the meaning changes, right? So you are now fixing A2. Sorry, you are fixing W3 and you are letting A2 move.
A2 move, yes, sir.
Right. So, see, this is some idea of this. Are you all able to get? Because I kind of confused by adding one more layer. And there are too many gradients floating around. Were you all able to get some picture of what is happening?
Yes, sir, it's much better compared to when I watched the video.
Okay, right. So, yeah. So if we try to compute dou L by dou, so we have computed dou L by dou W2, right? So we'll also have to compute at this stage dou L by dou A1, right? So we'll also end up computing dou L by dou A1, which will be what?
This thing into W1.
Yeah. So instead of A1, I'll have W1. Is that correct?
Yes, yes, sir.
Right. So please verify this. I am not verifying it now. Once you have dou L by dou A1, it's very easy to compute dou L by dou W1. Right. So see see, I think what Kaushik said the other time is it's a very good point. We have to be consistent in two things, right? If you always compute the gradient of the loss, right, which is what I think we are discussing in the slides also. So I'll quickly go through this slides part of it. Two layers. So these are the gradients we need: W1, W2, P1, B2. So this is the chain rule, right? I have just written it down explicitly here. So for computing dou L by dou W1, notice that I need the gradient with respect to A1, right? The activation one. So I compute that along with this gradient, right? I do this whenever I compute dou L by dou W2, I also do the A1 part. And then I back propagate this. I make
A1 part, how the second equation that comes below. Yeah, this one.
Yeah.
How did we get W2 out here?
So that's because dou L by dou, so instead of W1, it's A1, right? It's dou L by dou A1.
Right.
Sorry, we are here, right? So dou L by dou A1. See, dou L by dou A1 is what? Yeah, it is dou L by dou A2 into dou A2 by dou A1, right?
Right.
So dou L by dou A2 is nothing but y hat minus y. And then dou A2 by dou Z2 is G dash of Z2.
Right.
Z2 by dou A1 is W2.
Okay. Right.
Okay, so, and the whole idea of this thing is you make use of this in the next iteration when you're computing the gradient with respect to W1. Okay, I know this could have been done slightly better, but I'm sorry, this is one of the toughest parts in the whole of neural networks, right?
But whoever came up with this algorithm needs an applause.
Yeah, right.
He got more than an applause, I think.
Yeah, true.
Sorry, just so basically what you're saying is that each layer we are computing two sets of gradients. One is again with respect to the weight corresponding to that layer, and the activation output with respect to the previous layer.
Yeah, something like that. So in fact, if you look at the matrix form of the whole thing, we are computing three things at every layer. One is the first thing that we will compute is the gradient with respect to the activations, right? So see, the reason is like this. If you look at the forward pass, backward pass should be the reverse of that, right? So in the forward pass, what happens? We compute Z first, then we compute A, and then we compute the loss, right? So in the backward pass, what we do is we compute the grade. So if you want the gradient with respect to Z, then we need to respect A first, right? So I first compute the gradient with respect to A, then I compute the gradient with respect to Z, and along the way, I also compute the gradient with respect to W.
Right.
Right. So that's why I have written this in this order, right? First to do the activations. Once you know the activations, then A is just G of Z. So I can very easily get the gradient of the pre-activations. Once I get the gradient of pre-activations, I can get the weights, gradient of the weights. Okay, so these equations are the matrix forms, right? And they are actually not that hard, though it looks. If you're looking at it for the first time, it will be like totally confusing, right? So, but if you stare at it for a while, you'll understand. Is this notation clear to all of you? What's happening here?
What is G?
Yeah. So see, what we mean is this. We had one matrix there, right? So if I have, assume that this is my A, let's say this is the third layer activations, right? So there are 5 examples and 3 nodes are there, okay, in this particular layer. So these are the activations. Okay, so what I mean by A3 of G, right? G is it's a matrix of the same shape, right? But each element will be as follows. So is that clear what we are doing? This is nothing but the gradient of the loss,
Okay, the gradient of, okay.
right, with respect to each element of this matrix.
Okay.
Right. So see here, this corresponds to what? In the scalar case, this corresponds to this dou L by dou A2 or dou L by dou A3. Instead of a single scalar, we now have a matrix of activations. Therefore, we have a matrix gradient, a matrix of gradients. Yeah.
Right. Got it.
Okay. So likewise, you have matrix of gradients of pre-activations and for weights. So is this, are these three matrices clear what they are? Okay, assuming that is something you have understood, is the first equation kind of, are you able to comprehend this, what's happening here?
Sir, in case of regression, G is identity, right?
Only at the output layer, right? Assume, see, we are at the hidden layers now.
Okay.
So we have this in the first equation, you have the matrix of Z, which equals the matrix of the activation, gradients of the activation matrix multiplied element wise with the function of Z, the matrix of Z.
Not
gradient.
Gradient of Z.
Gradient of Z. Okay.
Right. So
why would we do this element? Okay, A into gradients of Z.
yeah, why do we do this element wise? Because the activation was applied element wise. Right. So if I go back to this, there is a nice picture here. See, Z was computed element wise, right? So sorry, A was computed element wise.
Yeah.
Therefore, when we go backwards, the gradients they also should be computed element wise.
Okay.
Okay,
So this, okay.
Since they are matrices, I need to multiply them, right? So element wise.
So how did this A giving the G of Z1 relate to this? This I'm not able to get, sir.
See, so this is, again, we have to follow the chain, right? So Z influences A via G, right?
Okay.
That is how we got. So it's like the power, this algorithm draws its power from this fact, right?
Right.
The influence of AL on the loss is the entire influence is consolidated in this one matrix.
Right.
The moment I have that matrix, the only thing I need to worry about is my activation function, right? So because that is all the dependence between AL and ZL are.
Right, sir. Right. And the second one?
Okay, the second one is actually, to understand this, you have to read this part, right? So if all of them are scalars, then what would it be? This is just dou L by dou W is dou L by dou W is equal to dou L by dou Z into A, right? That is what we do. Right. So for example, dou L by dou W is what? Dou L by dou Z into A1, right? That is what we had.
Right.
Instead of that, we have A transpose into dou L by dou Z, which is ZG.
Right.
Okay, so I know that this is kind of unnecessarily complicated, but
Just have to get used to this notation.
yeah, the notation is the thing. So one way to remember this is quite simple. You can remember this by following the shapes of matrices. Right. So A transpose, for example, will have to be one. So W has to be what? N cross SL minus 1 cross SL. And this ZL of G, if you notice, is common for both. So there's no transpose for that. So if the shapes have to match, then you can figure out whether this should be A transpose or A. right? Anyway, we won't ask you this in exam. We won't ask you to compute any of this. So only thing you have to know from the exam point of view is this is very simple to remember, right? So this at least we expect you to remember, but this is asking too much. We also know, so don't worry too much about this. Okay, so this is even more tougher in some sense. So the gradients with respect to output layer are like super tough. So I have two resources for that. One is a set of notes that we had for week 12. It was incomplete. Unfortunately, we couldn't do it for the entire course. So those who want to understand this in more detail can look at the appendix associated with this. So I've given some explanation on how this came about. Right. So if there are any brave souls who want to understand what this means, you can look at this resource.
So can you paste this on the chat?
Yeah. So this is
Thank you, sir.
and if you want to know a little more about differentiation and chain rule, for there is one thing for MLF, there was one write up. Okay, so this is the gradient. If you recall, this is the gradient for least linear regression, right? So this is xw minus y in some sense. So the reason I want you all to refer to this is this kind of is also relevant to the neural networks case, because this tells you this picture shows you how if you change a parameter theta1, how does it affect the loss cell, and so
Right,
this might be of interest to some of you. So I'll share this also. Anyway, so going back, I'm going to skip this part, okay, because explaining it is kind of tough. But the nice thing is that the gradients of loss with respect to the output layer it turns out to be a very simple expression, which is y hat minus y. That is all we need to remember.
Just as a side note, those matrices that you're talking about, they are like the Jacobian matrices. Is that what they call them?
Which ones?
The ones that you had shown earlier.
Yeah, they are the Jacobians. Yeah.
Okay.
Right. So they are. I think they come up in this derivation also, if I'm not wrong. But yeah, they are the Jacobians.
Okay.
Sir, here the y hat will change again, right?
Y hat will change as you keep passing different set of examples. Y hat will change. Okay, so see the essence of this. If you know it's that is also enough, right? Even if you don't know the individual things, individual gradients, how to compute them, the essence of it you must know. The essence is this, right? So backward pass is the whole idea of computing the gradients, right? Now, if you have y hat, then your gradient at the output layer is y hat minus y. And then you start from layer L and then go all the way back to layer 1. Okay, so you keep computing these gradients and keep going back and back. That is what back propagation is all about.
Sir, but you are not initializing that activation.
Which activation?
Sir, you wrote a formula for activation.
The B is, yeah, even the B you said will be initialized.
Right. No, see, this is just the algorithm for computing the gradients, right? So I have not yet started updating it. I have only found the gradients so far.
Can you go to the previous slide? So here, this AL of G equal to minus Y element wise multiplication of Y hat. This one, where are we doing this?
This is still gradients, right? We are still computing the gradients of the loss with respect to the output layer, output activations. Okay, so if you note, so why does it matter? See, what was the first thing that we did here? We computed dou L by dou Y hat, right? Unless you have that, you can't go back.
Yes, sir.
So likewise here, I need to compute dou L by dou final layer, which is what this A capital L G represents.
Okay.
Okay, so I need to start from the outermost layer and then keep going back. Okay, so I know it's a bit messy, but unfortunately that's the way it is.
Actually, what I'm saying is, so where are we using that AL of G, that gradient of AL equal to minus of Y, like in this formula?
To compute ZL, right? See, ZL influences AL, and in order to compute ZLG, I need to know what is ALG. Okay, I won't be using ALG in any other case. If you notice my algorithm, it doesn't require ALG, it only requires ZLG.
Yes, okay. So you are using ALG to find ZLG.
ZLG, yeah. So if I just tie this back to softmax regression. So in softmax regression, if you all remember, your gradient matrix was what? This was your gradient matrix. If you all remember, it was Y hat minus Y X transpose, right? Now all that I'm saying is A is softmax of ZL, right?
Right.
So in softmax regression, Z is what? Z is XW plus B. This is in softmax regression. In neural networks also, this is the same thing. And Y hat in softmax regression is what? This is what it is, right? And the gradient turned out to be X transpose into Y hat minus Y. So in the case of the output layer of the neural network, nothing changes, right? It's the same softmax. So instead of using X, I'm using A. I'm using A capital L. Instead of using Z, I'm using Z capital L. And this is Z capital L. I'm calling this is Y hat, right? This Y hat is also correct, but this is also A capital L. And I'm saying Y hat is actually A capital L. Right now, if I say, the gradient of the loss with respect to W is what? Same softmax equation should hold, right? So it's X transpose Y hat minus Y, correct? Nothing has changed. See, if you all understand softmax regression very well, then your output layer of a neural network is same as softmax regression. Okay, you can always make that contact. Okay,
for classification, no?
For classification, yeah, right. Some way to get back to this, right? So see, so this y hat minus y is what? This is what I'm calling, in the case of neural networks, this is what I'm calling ZL of G, right? And now you will see how the whole, I mean, still tough to see. I don't deny that. Right, the AL transpose ZL of G, which is what, if you notice, I'm computing AL transpose ZL of G. Right, it's pure softmax regression formula in some sense. In softmax, it was X transpose into y hat minus y. Here it's not X transpose, it's AL minus 1 transpose into y hat minus y.
Clear, sir.
Okay, so that is the gradients, right? So even if you understand 50%, it's okay. So once you have the gradients, all that you need to do is update the weights, right? So you get an X, you do forward pass, get y hat, compute the loss, compute the gradients, which is what the backward pass really is. This is your final algorithm, which is nothing but gradient descent, right? So for set number of epochs, for each epoch you do a forward pass, get the predictions from your network, compute the loss, compute the gradients, and update the gradients. Sorry, update the weights.
So again, one question:
Yeah.
how does gradient descent work in this?
Because it's not like you're saying, is it?
Yeah.
Yeah, so it will go and settle in some local optimum.
Okay.
Right, so we in neural networks we can never converge. I mean, we have maybe some global minimum exists somewhere, but we cannot have any guarantees here. We can have no convergence guarantees.
Okay.
Right, so if the loss, you see the loss plateauing after some set number of epochs, then you assume that that's the maximum you can extract from your network, and you stop that.
Right.
Okay, so is that fine? This is the net. Like this is what neural networks are about, basically. So one part which we have not mentioned is the initialization part, right? So this is another, I mean, there's vast amount of work on this also, but we are only mentioning a small fraction here. Why did we not initialize all parameters to 0? Or what happens if we set all parameters to 0?
Some complexity may arise, like log of 0, something like that.
Okay. Okay, so what will happen is,
Parameters or weights, you mean? When you say parameters, you mean
the weights, right? The weights.
Okay, okay.
So if all the weights are 0, or say some constant value, not necessarily 0, can you differentiate between this neuron and this neuron?
No.
Some constant value means they are same.
They are same, right? So there is a symmetry in this case, which is, if all the weights are the same, then my updates are also going to be the same.
Yes.
Right? So what will happen is, these neurons will kind of evolve in the same manner. Okay, so all the neurons, essentially it's like one neuron but replicated several times, 2 times in this case. But if you have 10 neurons, then same neuron replicated 10 times, and
it doesn't make any sense.
So, yeah, right. So right. You need neurons to learn different things.
Right.
Right. So it's a very bad idea to initialize everything to 0 or a constant. Typically we use
random.
some random. So there is a lot of work in this, right? So there are different kinds of initializations that have been tried out from different distributions. So you can refer to this link here in the slides. Okay, so there are research papers have been written about initialization alone. Okay, so we are just touching the tip of the iceberg here. We are just telling you that don't do this. So what should you do is something we have not discussed in this course. It's beyond the scope of the course, but that will be covered in the deep learning course.
So we are initializing here with the standard normal.
We are initializing with not sure if it's standard normal or typically standard normal, I think. Right, but there are some papers which talk about uniform initializing.
Okay, so that's also valid. Uniform.
Yeah.
Okay.
Right. Again, is there one best way to initialize? No, there is no such. There is no such rule, unfortunately. Okay, the final part before we close is overfitting, and if overfitting is probably one of the most important problems or issues with neural networks, because it's very easy to overfit neural networks, right? Here is a quick example of the number of parameters in a simple 3-layer network, right? If you have, say, if you take the MNIST data set, you'll have 784 neurons in the input layer, 10-way classification, right? So if you estimate the number of params, it will be close to 40K, right? So, and this is nothing, right? Imagine this ImageNet data set that we talked about last class that has 1,000 classes, right? And there are going to be millions of parameters in such networks. So we need ways to regularize these networks, right? So one is L1 and L2, which is kind of, we are used to it. In the context of neural networks, L1 and this L2 regularization is also called weight decay, right? You kind of decay the weights. So that's another alternate term used for this. But the other part is there is a new technique developed for which is specific to networks alone, which is called dropout. Right. So in dropout, what happens is that you randomly drop few neurons from a layer in every pass of gradient descent. Right. It's as though that those neurons did not exist at all. Okay, and then you train the network. Right. You keep doing this. So does anyone see why this method is going to work, or what is the use of doing something like this?
Your parameters will decrease, but I mean, if 39,000 we take half of them, then it's still quite a huge number.
True. See okay, so the reason why this works is that you're not going to drop the same set of neurons in every pass. Right? In every epoch or in every update of gradient descent, you're going to choose a different bunch of neurons and then drop them. Okay, so the network is kind of forced to learn with a reduced number of neurons.
Which means it won't overfit, does it?
Right. So these are all heuristics. Just see, these are two heuristics as given here. Okay, so you can think about whenever you drop out, you can think about it as a new network, right? Because certain number of neurons are missing. So you can think about dropout as a committee of neurons, a committee of networks, right? It's like you are training multiple neural networks at the same time. because you are dropping different number of a different set of neurons each time. You can think about, you know, training multiple neural networks and then averaging out the results of these networks. That is one heuristic.
No, this dropout you're saying happens layer wise, or we are doing for a certain sequence for one pass and then another sequence for another pass and then averaging it out.
Okay, so see, this averaging it is only a explanation. What we are doing is in each pass, in the hidden layers, we will drop out a certain number of neurons. That means they will be zero. Their outputs will be made zero.
So, and that'll be random.
And that will be random. The ones which you are dropping out will be random.
And they'll be half of the number of neurons in that particular layer.
So that is depend. Yeah, that is up to you to choose, right? What fraction you want to drop out.
Okay. Okay.
Right. But at inference, what you do is, see, at inference, what you do is you use the whole network, but whatever weights are going out from these hidden layers, right? You make them one half of their existing values, right? And that's because of this reason. Only one half was active anyways during training. Every time during training, what did you do? You drop half of them. Therefore, when you are using this network for inference, you should make sure that you multiply the weights by half.
So as you said, whether to drop half or not is based on our discretion. So if we drop half, then it is half. Otherwise, it would be that ratio, right? Whatever we've taken.
Yeah. Let's say only 20% you're dropping, then by that, you have to, you have to multiply by, I think, 0.8, right? In that case.
Yeah.
Because 80% would have been active during training. Okay, so in practice, what happens is that these are all so if you want to know what happens in practice, you have to go and look at a lot of libraries out there which implement this, right? So for example, if you go through this, it'll actually give you something which you'll be able to understand, right? So the dropout layer randomly sets inputs to 0, right? And here it scales slightly differently. Those which are not set to 0, it scales in a different way, right? So it's not too hard to understand these things if you go and check out these resources. But anyway, you'll be studying them in the next course in more detail. Okay, so the one thing you need to remember is that it's a nice point. The L1 and L2 that you are used to so far, it modifies the loss function, whereas dropout is a form of regularization that modifies the model itself, the network itself, right? So dropout doesn't touch the loss. Loss remains the loss remains the same, but you directly go ahead and modify the network. Okay, so that is the theoretical part of neural networks.
Hello, sir.
Yeah.
Sir, so can we say that when we are dropping out like a node, that means it will be a less load in the computational part,
I don't think we can say that, because see what happens is, if you look at the implementation, they effectively apply what is called a binary mask, right? So so whichever nodes are being dropped out, they are made 0, right? So the binary mask is nothing but 1 and 0, right? So you just apply that mask on top of the layer. I'm not sure if it will reduce the computational burden or not, and even if it does, may not be by a huge margin.
So what I understand you're saying is that it calculates for everything, only that mask makes that particular node 0.
0, yeah, yeah.
Okay.
Right. Any other questions? Okay, see, there are a lot of things we have skipped. We have not skipped. We have not covered because this itself is quite heavy. So if you are interested, then few resources are like this book that I briefly mentioned. It's written by this Michael Nielsen. So he's actually a quantum physicist. So his basic training is as a quantum physicist, but then he's a prolific writer. So you should read some of his works. He's one of the best writers I've seen, especially technical writing. So I'll share this also. It's a very readable book. The full code is there. You can also go to the code repository. Right, so that is one resource that you can use. All right, so any other questions? If not, we'll officially close the. Okay, okay then. So Saturday we are meeting again, right?
Go through the implementation, right?
Yeah. So Saturday is fine with all of you, right? Or do you have any?
Saturday is fine.
Fine, right? Okay. Okay then. Okay.
Thank you so much, sir.
Thank you, sir. Thank you so much.
Yeah. Thanks everyone. Bye.
Thank you.